Okay, so today's video is about predicting when a redox reaction is going to occur. And what we really mean by that is if I stick a solid piece of metal into an aqueous solution, will the ion in the aqueous solution be able to cause the metal to lose its electron, in other words, get oxidized? And so we've seen this in 9.1, where we put a coil of copper into a solution of silver nitrate. Now, silver nitrate, as we wrote the very first day, is colorless. So there's no color in here. It's just your copper sitting in a colorless solution. Then what's going to happen as time goes on is your copper starts to get this fuzzy look to it. So I'm just trying to make a little fuzzy. So just make your copper get really fuzzy like this. All right. All right. So just shade in the diagram in your notes there. And so the copper starts to get fuzzy. That's our first sort of observation. So in other words, what is that fuzzy stuff that is now all over the copper? Well, you don't have very many options because the only thing in the beaker is the copper solid, the silver ion, and the nitrate ion, and water. And that's basically all we have in our beaker. So what we're going to take a look at is, what is this? Now, through analysis, what we see is that this is actually solid silver. And let's label that right now. So what this actually is Ag solid. All right, so it's Ag solid. Now, what you should do is, where I have this observations and I have 1 and 2, put that over here in your notes to the right of the beaker. We have some space there, and right at the top, observations. And then for now, just write number 1. And so, I don't know if you want to pause the video right now, but give yourself a second and write this right there. Up here is where you'd write it on your page. Okay, so what I would do on your page is, what I'm about to write, I would put it underneath where you have written this sort of sentence. And what is going on for the copper to get covered in silver nitrate? So what we'll do is, I'm going to draw an arrow. You write what I'm writing underneath right here in your notes. So the reason is this. Ag, which was aqueous, has gotten an electron and become Ag solid. So there are fewer Ag pluses inside this second beaker here than there were when we started, because some of the silver Ag plus is now Ag solid. So this is what's happening in number 1. Now, the other thing that we notice is the solution starts to become blue in the second beaker. So I'll try to shade that in here. Let's see if I can shade this in. Okay, so you'll just have to label it on yours. But this solution starts to become blue. So I'll just shade it in. Now again, we have to explain what's going on here. Why is this solution all of a sudden becoming blue. Well, that's what we're going to look at in number 2. So we'll just label that. Let's change my color here to this. Get my pink color. So number 2 in your diagram, as I've written down here, solution becomes blue. So you can write this, again, I'd write probably on the bottom of your beaker. Solution becomes light blue. So we have to explain that too. What's going on here? So now I would write your second point, again on your page off to the side here. And let's take a look at the reason. What's going on? Well, the reason this is becoming blue is we know that copper plus 2 aqueous is blue. So somehow we've got copper plus 2 floating around. Now, in order for that to happen, we had to have a source of copper. Well, the source of copper was the bar. So the equation we're going to write now, and I'm going to try and keep my arrows lined up, is copper solid went to copper plus 2 aqueous, and this is blue. Now we're going to add 2 electrons here because we want this whole reaction to, you want the left side, which is neutral, to add up to the right side. So having 2 electrons now makes it neutral. So that's what's going on in number 2. We can draw a little diagram and just sort of put the pieces together in our first picture here. Now, the way I like to do this is I like to use sort of a scenario of where one thing is trying to be the bully and the other thing is trying to be the victim. So what's happening here is Ag plus is going up to copper and saying, give me your electrons. And copper has to oblige, and it gives up its electrons to become Cu plus 2 aqueous. And so what does Ag become? Ag now becomes Ag solid. And it's just what these reactions are saying down here. When Ag gets an electron, so this electron is one of the electrons that the copper here gave up, and then it becomes solid. So you see this equation isn't balanced. That's because in a balanced equation, and if you look on in 9.1 in the balanced equation we had there, is that one copper will give up 2 electrons, which means 2 Ag pluses will become reduced from plus to Ag solid. So 2 Ag pluses take these 2 electrons to become Ag solid. So you'd have more silver. Okay. If you look, and that's sort of the basic design, and you did this experiment last year, I'm sure. You just called it something different. You called it the activity series. And that's kind of what we're sort of looking at it, but we're looking at it, I think, a little bit differently than you did last year. So if we take a look at the next diagram that you have in your notes there, you've got this right here. Now let's just, if you go back to your learning goals, you'll see that this is something that you'll have to be able to interpret. And from this diagram, can you make this little chart here? And that's what we're going to learn as we sort of go through this lesson. Let's just try to figure out what's going on with this chart, and so we can wrap our head around it. What we've got in this chart is a bunch of experiments that have been done. This was the experiment we just talked about. So what happened, if you look above, copper was put into a solution of Ag+. Ag+ went up to copper solid and said, give me your electrons. And because there was a reaction, that means that copper gave up its electrons. Then, in your second experiment, you get another beaker full of Ag+, and you put in Pb solid this time. So what's going on in that beaker is Ag+ is going up to Pb, basically saying, give me your electron, and because there's a reaction, Pb has given Ag+ its electrons. And the same with zinc. But when you go over to copper now, copper plus 2, oops, let me go back. When you go over to copper plus 2 now, you'll notice that there's only 2 metals that reacted. So again, let me just sort of describe what the experiment would be. You now have a beaker of copper plus 2. You put a piece of lead in, and copper plus 2 goes up to lead and says, give me your electrons. And lead does, because it says we've had a reaction. So it says right here, reacts with. And the same thing with zinc solid. Copper plus 2 zinc was put into a solution of copper plus 2. And copper plus 2 went up to zinc and said, hey, give me your electrons. But you'll notice what's missing is Ag solid. Because you did that experiment, you put Ag solid into copper plus 2, but when copper plus 2 went up to Ag solid and say, give me your electrons, basically what silver said was, no, I'm stronger than you. You're not going to have the electrons that I have. And that's why there was no reaction. So if you were to look at that beaker, you would just have a piece of silver sitting in a solution of copper plus 2, which would be light blue, forever. So what we're trying to do here is build who is the strongest at keeping their electrons and stealing their electrons from other metals. So if we look way down here at Zn plus 2, the experiment that we would have done here is we would have taken silver solid, copper solid, lead solid, and zinc solid, and put them into separate beakers as Zn plus 2. And what you would have seen is, well, nothing, because zinc plus 2 cannot go up to silver solid and say, give me your electrons, and silver would oblige. Zinc plus 2 goes up to copper and says, give me your electrons. Copper says no. Zinc goes up to lead and says, give me your electrons. And lead has said no. And that explains, why there is a number of reactions. So the reactivity order, and this is what you guys did last year, was the reactivity series. Ag+ was the most reactive. It caused the most reactions to occur, and Zn plus 2 caused the least, which in this case was none. And so I'm not sure if you have to write that in your notes right now, but since Ag+ react with all the elements, Cu solid, Pb solid, and Zn solid, it has the greatest tendency to gain electrons. In other words, it is getting reduced. Remember, if you gain electrons, you become reduced. And so what this chart, let me just write that there. Well, I've written it here. What this chart is let's try to look at this chart and see how it sort of corresponds to that table up there. You'll notice that whenever we had Ag+, it was able to go to something under it and say, give me your electrons, and it had to do it. So Ag+ was able to go up to, so Ag+ here was able to go up to copper solid and say, give me your electrons, and copper did. So this electron would have come from copper. It was able to go up to Pb and say, give me your electrons. It was able to go up to zinc and say, give me your electrons. And that's what it's saying up in the chart up top when it says it reacts with. Now let's take a look at the opposite situation, zinc. Zn plus 2 is at the bottom of our list because it has the weakest ability to gain electrons. It's not good at gaining electrons from the things in this list. So the experiment was Zn plus 2 goes up to Ag and says, give me your electrons. And silver says, no. So there's no reaction. So zinc went up to copper and said, give me your electrons, and copper said no. And then zinc went up to Pb and said, give me your electrons, and Pb said no. So this is sort of a list of who is the biggest bully. So if you want to use that sort of terminology, don't use it on a test. In this scenario, with these four metals, this would be the biggest bully, meaning it can steal the electrons from the other metals, and zinc down here would be the biggest victim. Now, we don't use those words, biggest bully and biggest victim, in chemistry. That's just sort of my analogy. What we use is strongest oxidizing agent. So the strongest oxidizing agent here, Ag, is Ag+. Now, what we mean by strongest oxidizing agent, remember, the strongest oxidizing agent gets reduced. It's able to go up to another metal and say, give me your electrons. And so the weakest oxidizing agent is zinc, because it doesn't have the ability to, in this list anyway, to steal electrons. So we'll summarize that on the next page. But there's one more thing I want to add here, just to this sentence. So I've said it already, but I just want to sort of complete the circle. Therefore, it is the strongest oxidizing agent. And often we just call it S, I don't know why I won't leave it right there, SOA, for strongest oxidizing agent. Now, if you look in your notes, you're going to find a page, we'll call it the big list if you'd like, but it's Appendix C11. So if you want to flip a couple pages ahead, I think, you'll find Appendix C11. I might have put it in after 9.5, so I can't remember how I did it this year. But take a second now and find C11. And what that is just a giant list of not just metals, although we're just going to focus on the metals and their ions, but a giant list of chemicals that when you put them together, you'll be able to figure out, will there be a reaction? In other words, can one compound or metal or ion, I should say, take the electrons from something else? And so I'm sort of going to summarize what I've already done on the next page with this chart. So this is basically the same chart as above, but it is sort of written in the same form as Appendix C11. Appendix C11. All right, in your notes. And so if you read the definition there, that a spontaneous redox reaction occurs only if the oxidizing agent is above the reducing agent in a table of relative strengths of oxidizing and reducing agents. Quite a mouthful, but I think we can break this down into something a little bit simpler. So, first of all, here's what it's saying. If you've got an oxidizing agent, and you mix it with a reducing agent that is lower on the list. Now remember, an oxidizing agent is going to cause something to give its electrons. So that's the biggest bully. The reducing agent is going to give its electrons. So it's sort of the biggest victim. If you have this scenario where OA is above RA, you're going to get a spontaneous reaction. And what we mean by a spontaneous reaction is exactly what we have in 9.1 when we put that coil of copper into some silver nitrate, or at the top of this note on the previous page where you put a piece of copper into some silver nitrate. That reaction will occur by itself. You don't have to encourage it. You don't have to add any heat. It will just happen. And that's what we mean by spontaneous. So the best way to do this is with an example. And we've already talked about on the previous page. What it's saying is that if I took Ag plus AQ and I put into it Zn solid, the question is there going to be a reaction? Well, what you need to know is, well, there's two things. You can do an experiment and get your answer, or what you can do is look at one of these lists, Appendix C11. And that's what I'm trying to show you, is how to use Appendix C11. So the scenario is this. I've got, going up to the chart here, oops, right here, this is my oxidizing agent, because it's higher on the list, and it's going up to the reducing agent right here. So Ag is going up to zinc. We'll call this 1. You'll see later I'll put the 1 somewhere else. So it's going up to the zinc and saying, give me your electrons. Now, because zinc is lower on the list, it has to give up its electrons to silver. So going back to the reaction down below, we'll call this reaction 1, and that corresponds to the 1 in the chart up there. There is going to be a reaction. So silver is going to become a solid, and zinc is going to become aqueous. Now, it's not a balanced equation, but you get the idea. And so you see that this has been reduced, and this has been oxidized. And remember, if you get reduced, you were the oxidizing agent, and if you're oxidized, you are the reducing agent. And so now you see how what this OA-RA business is all about. Now let's look at another scenario where the chart's sort of going to look like this. And that's going to be a non-spontaneous reaction. Meaning nothing's going to happen if you just put them together. Forever they will just sit there. And we're going to call that, let's see, I'll put a little lower this time, number 2. Now up on our diagram, the scenario that we have going on here is now I have zinc plus 2 going up to silver. So we'll draw our arrows sort of that way. All right. So zinc is going up to silver. We'll call that 2. And saying, give me your electrons. Now, because silver is higher on the list, it has a stronger hold on its electrons. There is not going to be a reaction. So how that looks down here with number 2 is we've got this time Zn plus 2 going up to Ag solid and saying, Ag solid, give me your electrons. But because Ag is higher on the list, it's not going to give up its electrons. So we would just write here Nr for no reaction. Okay, so the last thing we're going to do, and I think this is the second learning goal, it's definitely one of them, I don't have the learning goals in front of me, is we want to make that table that we've seen on the previous page. So it's kind of like last year when you guys did the experiment with the activity series. Which one's at the top of the list, which one's at the bottom of the list. The way our list is going to go, though, is we're going to say who's the biggest bully, they're going to go to the top of the list, and who's the biggest victim, they're going to go at the bottom of the list. So these are some experimental results. So we're making that list, just like someone had to make that big, huge list C11 by doing some actual experiments. So here's how, one way I'm going to show you how to sort of, piece this together. let's take a look at the first reaction here. What you see is copper plus 2 has gone from plus 2 to 0. Now the only way to go from plus 2 to 0 is that Cu had to get 2 electrons. So what I would write over on this side in your notes is just what's actually happening here is CO gets the electrons. Like this. Okay, that's great, but what does that have to do with our list? What that means is that CO plus 2 must be higher on the list because it has gone to something lower on the list, IN, and said, give me your electrons. So our sort of conclusion here is CO is above IN. And then what I like to do, and I'll just do this sort of off to the side, is just somewhere, just do a little sort of sketch that, okay, I've said CO is above IN, so let's just over here somewhere say, okay, I've got CO, and it's going to be above IN. So CO is stronger than IN. Let's take a look at our next reaction. Copper has gone from plus 2 to solid. So again, it has gained 2 electrons. And CO has given up 2 electrons to go from 0 to plus 2. So what does this mean? This means that Cu plus 2 gets the electrons. And if Cu plus 2 gets the electrons, Cu has to be above CO. That's our conclusion, because it's stronger, got the electrons. So then down here in our list, Cu must be above CO. And you'll notice that if I asked you, well, which is stronger, Cu or IN, you don't see that experiment up here anywhere, because you don't have to do it. If you know that CO is stronger than IN and Cu is stronger than CO, then Cu is stronger than IN as well. So it's just higher on the list is stronger. So we're just developing this list. So the last experiment, what we see is Cu2 plus and PD. So PD, you'll see is, well, you'll see it's going to be highest on the list, because here's what happens. Copper plus 2 goes up to PD and says, give me your electrons. And it says here no evidence of reaction. In other words, PD did not give its electrons to Cu plus. So the sort of interpretation we'll write over here is, if we had no reaction, the ion, Cu plus 2, cannot get from PD. So what's our conclusion there? PD is above Cu. And in our little sketch here, we'll just put PD is above Cu. So in this example, it kind of worked out that I just kept piling on. I kept building my list up. Sometimes you'll do one and you'll find that you have to insert PD maybe in between here or something like that, and that's okay. This is sort of your rough work. So how you want to sort of present this, and this is what I'd want on a test, is in this form. And you'll see that this is really how it's presented for the metals only in C11. Is you have your metal ion, and it's like the chart we've already seen above on this page. Plus electrons forms the metal in solid form. Like this. So we're just going to make a little mini C11, like if you look at the top of the page at table number 3. We're just making one of those. Now I'll warn you now, don't always, I give you a question like this, and then all you do is go look at C11 and figure out what's above it. I will make up experimental evidence reactions so that it has nothing to do with that chart. So don't ever, if you get this question, just go looking at your appendix C11, which of course you'll get on the test, and just copy it and sit and figure it out, because I will change the results and you'll know it'll be one of these questions. Other cases, what I've done is I've just put X, Y, and Z. I just use letters in the alphabet, so they don't mean anything, and they're not on that chart. So be careful. This is how you want to do it, the analysis that we've done so far. And now all we're going to do is put the metal ion, so this is the aqueous form, and turn it into its solid. Now, for PD, how do we know what its ion is? What's P? Is it PD plus 1, PD plus 2, PD plus 3? If I give you a metal like PD in this case where you don't know what it is, make it up. That's not the point of the question. So we'll say, and I'm not even sure if this is true, pretty sure it's true, but let's say PD is plus 2. So it's going from its ion form to its solid form. Well, how many electrons do I need so that both sides are neutral or add up to 0? Well, I need 2 electrons in this case. And that was first on my list, so that's why PD goes first. Next on my list is copper, so I just want to write more formally that we started with copper plus 2, added 2 electrons, and it would become copper solid. Next on my list is CO, and we see above that it is plus 2 as well, and it's going to become copper or cobalt solid. And lastly is IN, and it is plus 3. So we need 3 electrons to make it IN solid. And that's how we, if you look in your learning goals, that you develop a table of redox strengths using 1, what I've got here, just reactions, or 2, like I did on the first page, is in the form of a table. And you'll see how this is important. You guys depend on this idea of oxidation reduction every single day. And we'll talk about that when we get to our next section, 9.5. What's the use of something like this? And you'll see that it has a use that you do use every day.